Everyone, good morning. Welcome to this section. Once again, we are meeting, and this morning I hope to continue from where we stopped that time. The topic is AC circuit, as we know before now, and the word AC. We already know that AC means alternating current in the current study, and so we want to consider this time when an alternating current is connected to a capacitor, that is a circuit device, a resistor, another circuit device, and finally an inductor alone. Then thereafter we shall consider what will be observed when the alternating current source is connected to all three circuit components or elements. So first of all, before we go on to describe the behavior of these components, we need to do an overview of what we have done before, and then we have to start from this point, the root mean square, or the effective voltage or current. I placed there on the screen the effective voltage, but more often we'll say the effective current. Now the root mean square current, also known as effective current, is defined as the RMS value of an alternating current is the current that would cause the same heating effect in a resistor as direct current from a steady source. So we have already seen the diagram of an alternating current before, the waveform. We observe that in periods, the current rises and falls, and and as such, we have the peak value of current, as you can see now, I naught. And here I think there's a little bit, there's an each here. I ought to have added the RMS value. So this I naught is connected to the RMS value, and the I ordinarily should be for the instantaneous value of the current according to the waveform that we have seen before. So this one is IRMS current, the root mean square current, which is the effective current that will flow through a resistor, causing heating to happen, and is given as the peak current divided by the square root of 2. Similarly, the peak voltage is V naught, while the RMS voltage is V naught over root 2. So these are the simple equations that simply represent the effective current of an alternating circuit system. Here we have the alternating current connected to a resistor alone. You can see the resistor R of value R, okay, and here is the alternating source. So you can see in the diagram, these lines they represent the wires, and then when this alternating source is connected, the current I and instantaneous current I will flow along this wire through this resistor, and the instantaneous current is observed to have a value of I naught sine omega t, and this is exactly the same form as the voltage applied sine omega t. So the phase angle, the angle of the sine angle here is omega t, which is theta. Theta is equal to omega t from rotating component. Of course, we understand what we mean by rotating component. The alternating current is formed from a generator. Of course, we learned about generator the other time, how they rotate a magnetic field to produce what EMF according to first Faraday's laws of electromagnetic induction. But that's not what we are dealing with at the moment. We are just telling us that this generator came from that concept, induction. So as a result, the components of the current is always rising and falling, given that will give rise to an instantaneous value of current, and likewise the voltage source is an instantaneous. In fact, it is the voltage that generates the current, And we can see that since the voltage is sine omega t, the current generated through this resistor, the current I is sine omega to t too. So that means both current I and voltage, we say they are in steps or phase. And then they are in phase if we need to write the Ohm's law connecting the current and voltage. And if we do that, we are going to get a result like this. The resistance R is equal to V naught over V over I naught, sorry, and the MRS over, we can also show that from V naught over I naught, then the resistance R can of the resistor can also be V RMS over II RMS. So take note of this. So we turn now from here to the next one. When the system is connected to a capacitor, this is to a capacitor, yes, this is when it's connected to a capacitor. Now when the alternating current system with the same voltage V naught sine omega t is connected to a capacitor alone. This is the symbol for the capacitor, one positive, the other one negative, as the case may be. Now when this happens, the applied voltage you see is V, and is equal to V naught peak voltage sine omega t, and current flows in the circuit around about. But this current that is generated by this system is ahead of the voltage. Now according to some deductions which are not shown here, some proof, it can be shown that the current that flows through this system is given by I naught sine omega t plus pi over 2. The value pi over 2 means 90 degrees. Of course, we know that pi is angle that is measured in radian. So if we convert pi over 2 to angles in degree, that will give us 90 degrees. So that there is an extra angle in the angle part of the current. Apart from omega t, we also have an additional angle plus a positive, take note of the sign, plus pi over 2, that means plus 90 degrees. That means when the current has traveled, when the voltage has traveled an angle of omega t, the current has traveled an angle of omega t plus pi over 2. That means the current has an extra angle of pi over 2 ahead of the what? Voltage. So that means we can say that when an alternating current is connected to a capacitor alone, when an alternating voltage rather is connected to a capacitor alone, the source voltage will lag the current, or in a different language, you can say that the current will lead. The current will lead the voltage by 90 degrees, and this is described by the equation. As you can see, we've been pointing this equation for some time now, and now the capacitor has a property analogous to the resistance of the resistor. This property is known as the capacitive reactance. This capacitive reactance behave like the resistance that the resistor has, because it is this property that enables the capacitor, that is this capacitor, to oppose the flow of current through it, just like the resistance of a resistor tends to oppose the flow of current through the resistor. So this property of a resistor that look like the property of a resistor called resistance, this property of the capacitor is called capacitive reactance, and is denoted by the symbol X subscript C, XC, and XC is given by, and after some deductions and relation between the current in sorry the voltage and the current generated by the voltage source, it was found that this capacitive reactance, when written in Ohm's form, in analogy to the resistor, it is found that this capacitive reactance, which is like a resistance of the capacitor, is given by the peak current voltage rather divided by the peak current. This is in harmony with Ohm's law, and which we can also write as the RMS voltage over the RMS current through the circuit if the source is connected to a capacitor alone. But after some rearrangement, this formula, after some rearrangement, you can we notice that after some rearrangement, we see that uh, after some rearrangement, uh, we have an equation, underlying equation, which says that which says that the capacitive reactance is equal to 1 over omega 1 over omega c. This is not c, it's c. 1 over omega c, where 1 over 2, where omega is 2 pi f, where f is frequency. All right, so it is 1 over omega 1 over omega c, 1 over omega c. And when we change this omega to pi, to angular frequency, to frequency in terms of frequency, pardon me, we have 2 pi f, where f is frequency, and c here represents the capacitance of the capacitor. Please take note, capacitance of a capacitor is different from capacitive reactance. Capacitive reactance is derived from the capacitance by applying this formula. The capacitance of a capacitor is represented by the symbol capital letter C, or simply C, and the capacitive reactance is represented by the symbol capital letter X with a subscript C to indicate that it is a capacitive reactance. Please, while capacitive reactance is a kind of resistance, capacitance of a capacitor is a, is describing the ability of a capacitor to store charges. Of course, we know that a capacitor is a device that stores electric charges or electricity. So take note of that. We shall use this formula in subsequent uh, lessons. So take note of these formulas. Without proof, we do not need the proof at the moment. It's the application that counts for us at this time. So now we turn to the case of an alternating current connected to an inductor. We have seen the alternating current connected to a resistor. We have seen the alternating current connected to a capacitor. And now let us turn attention now to the alternating current connected to a simple device that looks like a coil, but it's called an inductor. Now, in this study, the inductor is represented by the symbol L, and the unit of the inductor is simply the Henry. We shall see more of that when we take examples in our next class. But mind you, examples will be pasted on this on the classroom, and all students should do well in their leisure time to go get the examples and study them accordingly. So here we are back explaining the connection of an alternating current source. As you can see, this is the symbol of the alternating current source connected this time to an inductor. What will be the result? Now, we find out that in the previous study, when this source was connected to a capacitor, the current was ahead of the voltage, but yet it is not so. When the alternating current voltage source V naught sine omega t is connected to an inductor, this time we will see that the current that will flow will be having a negative value of minus 90 degrees in the angle path. That tells us something. If the voltage is having an angular path of an angle part of omega t, and the current is having an angle part of omega t minus pi over 2, it means omega t is subtracting pi over 2. So you are removing 90 degrees, or we are removing 90 degrees from omega t in the case of the current. While in the case of the voltage, the angle remains omega t. So that means the current is 90 degrees below or behind the voltage. Here, with proper language to use is to say that the current lags the voltage, or better off, the voltage leads the current by 90 degrees. So take note here we have reserved pi over 2 as the symbol for a 90 degrees in the expression or equation seen. And also after some rearrangement, it is found that the inductive reactance, just like we have the capacitive reactance, which is a property of the capacitor that tends to oppose the flow of current in a circuit, we also have a property of the inductor called the inductive reactance. All right, we have the capacitive reactance, we have the inductive reactance. This property of the inductor that tends to oppose the flow of current in an electric circuit, that property is called the inductive reactance. It is just like a resistance. Is that the resistance like that of the compared with the capacitor? That is, it is directly analogous to the capacitor, but it is generated in the system by an inductor. That's just the difference. But take note, all resistances are measured in ohms, whether it is capacitive reactance, inductive reactance, or the resistance of a resistor. All three rather, are units. They have units called ohms. Ohm. The unit of resistances are generally the ohm. And we must note two of them, the capacitive reactance and the inductive reactance. These ones, they are not pure resistance, they are imaginary resistance. In our subsequent lesson, we will understand more on the concept of this resistance called reactances being imaginary and not pure resistances as they are. So thank you so much for listening to this section. Do well to check for the examples that will follow, and by the grace of God, next meeting we hope to conclude this topic on alternating current, and then we shall be dealing with the alternating current connected to all three circuit elements: a capacitor, resistor, and inductor in series. The connections will be in series, and they will also consider when any of the two components are connected: a capacitor and a resistor, and a resistor or a capacitor, or perhaps an inductor and a capacitor. With this, we have come to the end of this section. We shall continue next time. Thank you for listening.